How you deal with?
What is going on, everybody? It's your boy Average Leader here with another video, and today we are tackling number 332, Reconstruct Itinerary. As you can see, this is the second most asked graph problem out there, and in fact, it's commonly asked by Uber, Amazon, Twilio, Bloomberg, Facebook, Microsoft, Intuit, Expedia, and a few other of these companies. If you guys can go ahead and hit that subscribe and like button, that would mean the world to me. It helps my channel out a ton by giving it more exposure to people that don't know me. And if you want to see another problem done, just comment down below and I'll make sure to do it for you. And with that all out of the way, here we go. You are given a list of airline tickets where tickets of index I equals from I to I represents the departure and the arrival airports of one flight. Okay, so let me see here. So we have these tickets here, and then each of these inner lists represent the from and to airports. So we're going from MUC to LHR, wherever those are. Okay, and we need to reconstruct the itinerary in order and return it. Okay, so that's not too bad. All of the tickets belong to a man who departs from JFK. Thus, the itinerary must begin with JFK. Okay, so that makes things a little bit easier. We have a starting point. If there are multiple valid itineraries, you should return the itinerary that has the smallest lexical order when read as a single string. For example, the itinerary JFK LGA has a smaller lexical order than JFK LGB. Oh, okay, so whenever we have to break ties, we need to break them such that we are picking like the lexicographically smaller itinerary. Okay, and you may assume all tickets form at least one valid itinerary. You must use all the tickets once and only once. Okay, so this is actually a lot to unpack when reading through the problem for the first time. It's actually very intimidating, I'm not gonna lie. But I think when we look at some of these examples, it's a little bit easier to see what's going on. So let's look at example 1 and 2 on the iPad. So I took this example straight off of Leetcode. This is example number 1. And you know, the first time I saw this problem, I actually thought that because we were given this graph representation, which, you know, that was a big hint from Leetcode's perspective. Like, they gave us like a graph, so it made me already think, okay, so we should probably start like representing this as a graph. So because we had a graph from the get-go, and because we had these tickets which represented a before and after airport, like we'd go from JFK to MUC and MUC to LHR and whatnot. Because we had these before and after airports, or almost, you can almost look at these as like they were rules. And for me, if I know that I have a graph, and if I know that I have a set of rules I need to follow in order to get some type of ordering, I immediately go to trying to code out a topological sort for this type of problem. And you know, looking at this output right here, this actually looks like a topological ordering for this graph right here. But when I go to example number 2, I get this graph right here. And for those of you guys who don't know what a topological sort is, I actually go much more in depth in my course schedule 2 video. And when I saw this problem, I also said to myself, like, oh wow, this is very similar to course schedule 2. So that also kind of like got me thinking I need to use a topological sort. So go watch that if you want to learn about topological sorts and stuff. But when I look at this example here, I see that we have a few cycles in this graph. Specifically, this one right here, we have JFK to SFO to ATL. Now, we cannot do a topological sort on a cyclic graph. Topological sorts can only be done on DAGs, or directed acyclic graphs. So, you know, my topological sort hypothesis doesn't really work in this situation. So the next thing that I did was I looked at the output here, and I tried to figure out how we could get this output in this order. And because we're told that we have to start at JFK, I just kind of traced through this output with the graph that was provided to us, and I noticed something pretty interesting. So looking at this graph, we go from JFK to ATL, and this represents these two elements in our output. And then from ATL, we go to JFK. So using this bottom arrow, we go from ATL back to JFK. and that arrow represents these two. Then we go to JFK SFO, and then we see that there's an arrow connecting JFK to SFO, and that handles these two. And then from SFO, we go to ATL, and that's represented by that arrow. And then ATL to SFO, that's represented by this other white arrow. So once I realized that we can get through all of these outputs by following each of these arrows, specifically in a depth-first search manner, I realized that this was just a DFS problem. This is just a depth-first search problem. And that makes things so much easier, because now all we have to do is, really just implement a DFS. The only thing that's a little bit different here is that this DFS goes to the lexicographically smaller node before going to the larger one. Or in other words, if we had JFK here, we see that JFK goes to ATL before we go to SFO, right? So in other words, we're going to the alphabetically smaller element here, or the smaller node here. So the real question is, how are we going to represent our graph in a way such that we go to the lexicographically smaller element first in a tiebreaker type situation? Well, the first thing that I thought about was, okay, how do we normally represent our graphs? In code, we normally represent our graphs like this. We say our graph is a hash map, where the key represents the type of each of our nodes. So in this problem, each node type is a string, and the value is usually an array list of the type of each node, so string. And this array list just holds the neighbors of each of our string nodes. So for instance, normally we'd have a graph where, let's say we had JFK as the key. The neighbors would just be SFO and ATL, and just, in no particular order. If I could have put ATL, SFO, but it's completely random at that point. So is there a way where we can hold our neighbors with this ordering, this alphabetical ordering in mind? Is there a data structure that we can use that has this ordering property? Well, if we used a priority queue instead of an array list, that is the way where we can get our ordering that we want. So I'm going to use a priority queue. And just for those of you who don't know, if we stored all the alphabets in a priority queue, A through Z, at the top of that priority queue, we would have A. So if we polled at the top of that priority queue, we'd have A. And if we polled again, we'd have B, then C and D, and so on and so forth. So we would have an alphabetical ordering using a graph where we store the neighbors in a priority queue. So with that being said, what would that graph look like? It would look like this. So in here, we'd have a graph hash map where we'd have the keys JFK, SFO, and ATL. And fun fact, I actually live in Atlanta. I live in ATL, so there's a little fun fact for y'all. And in our priority queue, because we have everything alphabetized, we can store these neighbors like this. So JFK, what are the neighbors? We have ATL and SFO, so I'm going to store them in alphabetical order. And then SFO, we have ATL only, so I'm going to store that here. And then ATL, we have JFK and SFO, so I'm going to store that in order because we have a priority queue here. All right, now we have all of our pieces, right? We have our graph, and we know that we have to DFS from JFK, and every time we're performing another iteration of depth first search, and when we're picking the neighbors we want to DFS on, we're always going to pick our neighbor in alphabetical order. So in JFK's case, we're going to pick ATL before we pick SFO. So now what I'm going to do is I'm going to do a DFS on JFK and using this graph that we have here, and see if we can get the output that Leetcode has provided for us. So I'm going to move this output right here, and I'm going to make it a little smaller so we're not taking up too much space. All right, so now what I'm going to do is I'm also going to have this result variable that's going to hold our ending result here. So let's do a DFS on this thing. So we're told that we have to start at JFK. So looking at JFK here, we know we need to DFS on one of its neighbors, either ATL or SFO. And looking at JFK in our graph, we see that its neighbors are ATL and SFO in that order. So what we're going to do is we're going to pop off or pull an element from our priority queue that we have here. So I'm going to pull ATL, and every time I pull an element from our priority queue, that is going to represent the node that we're going to DFS onto. So since we pulled ATL, I'm going to DFS onto ATL, and that's going to be our first iteration of our DFS. Okay, so now we're at ATL. So looking at the neighbors of ATL, we see that JFK is the first neighbor that we can DFS to, since that's what's in our priority queue. So we're going to pull JFK. So I'm going to pull this, and I'm going to go back to JFK. So this is going to be the second thing that we DFS on. Now we're back at JFK. So since we're at JFK again, we see that we've already gone to ATL, so we can't look at that again. But we have SFO. So now we're going to pull SFO, and we're going to go to SFO. So when I do that, that's going to be the third thing that we iterate onto. And now we're at SFO. We see that SFO only has an arrow going to ATL. So ATL is its only neighbor. So I'm going to pull ATL, and I'm going to go to ATL. So that's going to be the fourth iteration of our DFS. And finally, we're at ATL again. So the last neighbor that it has is SFO. So we're going to go back to SFO, and that's going to be our fifth iteration of DFS. Now, if you look at this order that we have here, JFK to ATL, and if we just like wrote out that result, we have JFK, and then from JFK, we're going to ATL. Then from ATL, we're going to JFK. So I'm going to hit JFK again. From JFK, we're going to SFO because that's our third iteration, so SFO. And then what's our fourth iteration? We are going to ATL, so ATL. And from ATL, we're going right back to SFO. So SFO I'm going to put right here because I'm running out of space. And notice this result equals the output that Leetcode had provided us. We're getting that same ordering. Now, there's one big question that we need to ask ourselves. And with DFS type problems, I usually mess up on this particular step. The question that we're going to ask ourselves is, are we going to add to our result before we actually iterate to the next neighbor, or are we going to iterate through all the neighbors, and when we recurse backwards, are we going to add to our result? So in other words, in this case right here, notice how I said, okay, so let's look at our iteration steps. So from step 1, we have JFK ATL. From step 2, we have ATL JFK. So, and that's the order that I put it in. So in other words, I basically put it in the order before we iterate through our neighbors. Now, if we coded this out, we are going to get some type of error. And if you said that in an interview situation, hopefully your interviewer will tell you to rethink that thought. Maybe they'll give you a hint, or maybe they'll give you a situation where that might not necessarily work out. So let's think of an example where that situation might not work out. So this was an example test case that I actually failed on Leetcode because I added to my result array before DFSing on my nodes instead of adding after I DFS on all my nodes. So in other words, my answer looked like this. So in that situation, we're going to start at JFK. So I'm going to have my result variable right here. And what I'm saying is, okay, so we're at JFK. So before we DFS any further, let's add it to our result, JFK. Now, we see that JFK has two neighbors. We have KUL and NRT. And because we're going to go to the neighbor that has a smaller lexicographical number than the other neighbor, we're going to go to KUL. Now, when I go to KUL, I'm going to add that to my result before doing any other DFS step. Now, I'm going to check its neighbors. Does KUL have any other neighbors? No. So I'm going to go back to JFK here. And now JFK, does it have any other neighbors? Yes, it has NRT. So we're going to go to NRT and add that to my result. Now, NRT, does that have any other neighbors? Yes, it has JFK. So now we're going to add JFK back to our result, and we'd be done here. But look at this. Our result has to be in an order such that our result needs to be in an order such that if we're looking at two airports side by side, there needs to be a connecting flight between those two airports, or else it's going to be an invalid itinerary. So looking at JFK to KUL, we see that there is a path from JFK to KUL, and I'm going to use another color here, JFK to KUL. Now looking at KUL to NRT, is there any flight that goes from KUL to NRT? No, there's not. So this would not work for us. This is actually an invalid itinerary. It's an invalid result. And remember, what we did here was we added to our result before doing any DFS onto the neighbors. So is there a way to combat this? Is there a way to get a correct answer while doing a DFS? Absolutely. What we can do is DFS through all the neighbors, and the last step that we can do before going backwards in our DFS and like kind of recursing back to a previous airport is that's when we can add our airport to our results. And I think if that didn't make a lot of sense, I think when you see this example, you'll see that this will make some sense. Okay, so I'm going to erase some of this stuff right here. Okay, so once again, I'm going to have my result array right here. We're going to start with JFK. So JFK, does it have any neighbors? Yes, it does. It has KUL and NRT. And because we want to go in alphabetical order when we're doing tiebreakers, we're going to go to KUL first. So we're going to go to KUL. Now, KUL, does it have any other neighbors? No, it doesn't. So when we do a DFS, we notice that this is the last step that we're doing here with KUL before we return back to JFK in our recursive stack. Now, since this is going to be the last time we see KUL, we know that we need to add this into our result at some point, right? But looking at this graph, we know that there's no way that we can go back to KUL once we've seen it already. So since this is the last time we see KUL, and after we're done DFSing through all of its neighbors and noticing that there are no neighbors of KUL, that's when we're going to add KUL into our results. And we're going to add it at the end, actually. We're not going to add it to the beginning and then append everything else onwards. We're going to add everything from the end and just going to keep adding to the beginning. Okay? And you'll see why we do this after I'm done with this. So now from KUL, we're back to JFK. Now, does JFK have any other neighbors? Yes, we have NRT. So from JFK, we have NRT. So we're going to go here. Now, does NRT have any neighbors? Yes, it has JFK. So we're going to go to JFK. Now, does JFK have any other neighbors? Since we've seen KUL already, and since we've seen NRT already, we don't need to iterate through those again. So right before we go back, we recurse back to NRT, we're going to add it to our result. So I'm going to put JFK into our result, and I'm going to iterate or recurse back to NRT. Now, does NRT have any other neighbors to recurse through? No. So we're going to add NRT to our result. And now finally, we're going to recurse back to JFK. Does JFK have any other neighbors that it has to recurse through? No. So we're going to add JFK to our result. And by doing this, this is the real key to the problem. Appending our nodes to our results after we're done DFSing through all of our neighbors and after realizing that there are no more neighbors to DFS onto, and also adding to the front of our results every single time. And that way we get a result that actually works. So look at this, JFK to NRT. We can do that. Let me erase some of this real quick. We see that we can go from JFK to NRT. And then from NRT to JFK, we can also do that. And then from JFK to KUL, we can also do that. So we're going through all of our airports. We have a valid itinerary through all of our airports. And we don't have an order where there's like gaps between airports, like KUL to NRT. We don't have that anymore. So that is how we are going to do this problem. Hopefully that made some sense. And now let's dive into the code. So first things first, let's figure out what we're trying to return. It says here we need to return a list containing string. So I'm going to return a list here, and I'm going to call it answer. And remember what we just did in our example on the iPad. We realized that we have to add to the front of our answer every single time, or we're going to add to the front of our list every single time. So between an array list and a linked list, what is more efficient time complexity wise? Well, if we had an array list and we kept adding to the front, we have to shift all those elements in our backing array to the right one to actually add to the front. But if we had a linked list, all we have to do is create a node and then like add that to the front, which would be an O of 1 time compared to the O of n time complexity at worst case in a array list. So what we're going to do here is we're going to initialize a new linked list instead of an array list. And let's also create our graph. So remember, our graph is going to be a hash map where the keys are going to be strings and the neighbors of each of our nodes is going to be a priority queue, not a array list that we're so used to seeing. And I'm going to call it graph, and I'm going to say equals new hash map. All right, so we've done that. And now let's go ahead and initialize all of our nodes in our graph to an empty priority queue, a new priority queue. So for list string tick in tickets, all I'm going to do is initialize each of the nodes. And what are the nodes that we're actually going to store here? Since we're trying to store the neighbors of each of our nodes, let's store the first airport, because this is the airport that we're departing from. And this is the airport that's going to have the actual neighbors, right? Because like MUC has the neighbor LHR here. MUC has the neighbor LHR. SFO here has neighbors ATL, and JFK has neighbors ATL and SFO. So we're going to want to put tick.get 0, because this represents the the from airport, quote unquote. And I'm also going to turn off autocomplete. I don't know why that's on. And what am I putting with each of these airports? I'm going to put a brand new priority queue. And this is going to initialize a bunch of priority queues for each of our nodes. And this is going to, remember, these priority queues represent the neighbors of our nodes, and it's going to hold the neighbors in alphabetical order, which is exactly what we want. So from there, let's actually build our graph. So and I'm just going to copy list, string tick in tickets again. And to actually build our graph, I'm going to get the from and to airports. Okay, so string from equals tick.get 0, and then string to equals tick.get 1. And because I want to make a direct connection from the from airport to the to airport, what I'm going to do is grab the neighbors of the from, and I do that by doing this priority queue string, and I'll call it neighbor equals graph.get from. And to make a direct connection from the from airport to the to airport, all I have to do is add to our neighbors and then store that back into our graph. So I'll do neighbors dot add to. And finally, I'm just going to store this back into our graph along with the from airport. So this is kind of like updating the neighbors of our from airport, and it's kind of updating our graph and actually adding that directed edge into our graph. So dot put from neighbors. All right, hopefully I didn't spell that wrong, because I always spell this neighbors wrong when I do these graph problems. But okay, look at that though. I mean, after those lines, after those quick 1, 2, 3, 4, 5 lines, we've built up our graph right here. And all we have to do now is our DFS call. So let's do a DFS, and what we're going to do is we're going to DFS on a specific node that we passed in. So the first node that we pass in is going to be our JFK, and we need our answer list to actually append our values onto, so I'm going to pass in answer as well. And we also need our graph, just so we have constant access to each of the nodes and their neighbors in our graph. So with these 3 parameters, let's go ahead and create our DFS helper method. So that would look something like this: public void DFS, and in our DFS we're going to take in a string, and remember each first parameter is going to represent the node that we're going to actually DFS on, actually search on. So we're going to take in node, and I'm going to also take in our answer list. So I'm just going to copy this in to here. And finally, we're going to take in our graph. So I'm just going to copy this in to here. All right. Now from here, all we have to do is grab the neighbors of our node here and just DFS on that neighbor. So it would look something like this: priority queue, a string, and remember I called it neighbor, or let's just call it neighbors, equals graph.get node. So now we have all the neighbors of our node that we'd like to DFS on, and since we have them in alphabetical order, we can just iterate through these neighbors and just do a DFS on them. So how do we actually iterate through the neighbors? Well, I'm thinking let's use a while loop here. And what are some conditions that we need? Remember, we pull from our neighbors, and after we pull from the neighbor, that is going to be the node that we're actually going to DFS on. So at some point, we know that our neighbors is going to have a size of 0. So while our neighbors dot size is greater than 0, and we also want to make sure that our neighbors isn't null, because in this situation, look at this, all of these 3 nodes here have some neighbors, right? But now if we looked at example number 1, we DFS on JFK, and then that'll take us to MUC, then we DFS on MUC, that'll take us to LHR, and once we DFS again, we go to SFO, and once we DFS here, we go to SJC. Now let's pretend that we're looking at SJC right now. The first line that we have here is we're doing graph.get SJC. But now we see that SJC doesn't have any neighbors, so it's actually going to return a null value. So let's also make sure that our neighbors isn't null. So while our neighbors does not equal null, and our neighbors.size is greater than 0, let's pull the first neighbor in our priority queue. So string, and I'll just call it 2 again, equals neighbors.pull. Yeah, that's it. And remember, since we're storing all our neighbors in a priority queue, this is going to be the lexicographically smaller neighbor amongst all of the neighbors that are in there. And now that we have this neighbor, we just want to DFS on that neighbor. So DFS2, and we're just going to pass in answer and graph once again. And just like we did in our example on the iPad, when do we actually add to our result? Well, we add to our results after we are done DFSing through all of our neighbors, right? So after this, all we have to do is answer.add, and since we want to add to the beginning every time, we're going to pass in 0, which is going to represent the index that we're going to add to. And what are we going to add at index 0? Well, we're going to add the node that we're on right now. So once we do that, that should do it. And finally, we can just return right here, but we don't really need this line. But I believe that is everything. That's how you do this problem. So hopefully this works when I run it.
They ask you how you are, you just have to say that you're...
Oh, of course. Made a mistake. That was a pretty dumb mistake right here. I just did graph, and then I put in tick.get0 new priority queue. What I want to do is graph.put tick.get0 new priority queue. So hopefully that fixed that. Can't find symbols while neighbor. Did I spell this wrong? Of course I did. What did I tell you? I knew it. I freaking knew I spelled neighbors wrong. So I also did that. Okay. Sorry about that, everybody. So neighbors. I knew I always spelled that wrong. So
fine when you're not really fine, but you just can't.
When I rerun it, oh, missing a return. Oh, duh, of course. So after we're doing this, after we're done with our DFS, see here we're adding to our answer that we're passing in here. So all we have to do after this is return our answer list that we have up there. So return answer. All right, let's run it. And boom, that is accepted. Let's submit it. My laptop just died. So yeah, we see that this is accepted. I'm going to submit it now. All right, look at that. We got a runtime of 5 milliseconds, faster than 78% of Java submissions. So this is pretty good. Let's talk about the time and space complexity here. So looking at what we did here, so we're just iterating through all the vertices and edges. So that's a linear time complexity right there. And here we're also iterating through all the nodes and edges. But every time we go through a neighbor of a node, we're actually storing that edge and vertice into a priority queue. And remember, every time we add to a priority queue, that is a log n time complexity. So every time we do this, we are actually inserting into our priority queue with a time complexity of log e plus v. So since we are iterating through all of the nodes, vertices, and edges, and since we had to add to our priority queue every single upon every iteration in the beginning, I believe our time complexity will be O of, here, I'm going to type this out. Time complexity would be O of E plus V times, and this would be in like parentheses here, times log E plus V. Since we have this, which is like a linear time complexity for when we're looking at a graph, since we're iterating through all the vertices and the edges, and we have to multiply log e plus v, since upon each iteration of us like building our graph, we had to store a node and its edge into our priority queue on every iteration. So at the worst case time complexity, our time complexity would be O e plus v times log e plus v. And our space complexity is a little nicer than this, since we only have a priority queue that's holding everything. At the worst case, it's holding all of our nodes and edges. So our priority queue, or our space complexity, would be O of E plus V, where E represents the edges and V represents the vertices. And that is it, guys. I hope this explanation made some sense. I feel like I wasn't on my game today. I think I stumbled a little bit more on my words today, so I'm really sorry about that. But yeah, guys, I mean, if you found any value from this video, go ahead and give this video a like and subscribe to the channel, and just let me know if there's any other things that I could do to improve. I really want to make the best possible content I can for you guys, so let me know if there's anything I can improve on. And if you want to see any other problems done, just comment down below and I'll make sure to do them for you. And yeah, guys, I hope you guys have a great rest of the day, and I'll see you guys next time.